so now back to what does this have to do with us as computer scientists? So here's what's really interesting. All right, so what have I tried to convince you? I've tried to convince you that similarity among genomes or subsequence thereof is totally fundamental in genomics. I've told you about what the sort of canonical definition of similarity is this NW score. And what's remarkable is that this definition is intrinsically algorithmic. Okay? Without fast algorithms, in particular for sequence alignment, this definition makes no sense. This definition would not be operational. You could not use it. Okay? I'll elaborate. So the definition of the NW score is inherently algorithmic. Without fast algorithms for sequence alignment, this definition would be, for all practical purposes, useless. Okay? Why? Well, you can't even answer the question of what is the NW score between two strings without computing the best alignment between them. Remember, that is the definition of an NW score, the quality of the best alignment between two sequences. So you need to find the best alignment to determine the NW score to answer the string similarity question. Okay? So big deal. So you need an algorithm to compute the best alignment. How hard could it be? Right? So we've got to align these two strings. There's some number of ways you can align them. Just go through them one at a time. Figure out the penalty of each of those alignments. Remember the best one. Trivial. So that algorithm's called brute force search. Sometimes in 161 we will struggle to understand whether a proposed algorithm is correct. This is not one of those occasions. Okay? This is a correct algorithm for computing the best alignment between two strings. So are there any objections? There's a lot of alignments. So someone seems worried this might take too long because there's too many alignments. But like, computers are so fast these days. Does it really matter?
Is there a finite number?
That's a good question, actually. Is there a finite number? So it turns out, if there's an infinite number, we'd certainly be in trouble. If you think about it, there's no reason to match a gap with a gap. So if the strings have lengths n and m, you'll never use more than the max of nm gaps in each. So it's not important if you didn't understand that comment. But there is a finite number of alignments that one only needs to try. Okay? And computers are fast, so it should be fun. Yeah?
Genomes are like humongous in comparison with data.
True.
I mean, it's just vast.
That's true. So the suggestions are maybe computers aren't fast enough to handle this. Maybe either the data is too big, or maybe the number of alignments is too big? Well, yeah, I agree, actually. So that's a good point. And that's the problem. Let me make this a little more concrete, or stark, perhaps. So the number of possibilities you would have to check, in other words, the number of alignments, even after you do the obvious pruning, the number of alignments through which you would have to enumerate to complete this for loop actually starts exceeding the estimated number of atoms in the known universe. Not even on big data sets. We don't even have to use the big data set objection. It's a legitimate objection, but I don't even need it to make this point. Even for string lengths in the 100s. So Moore's law will not save you. Right. And in fact, the running time would be prohibitively slow even for extremely modest-sized strings, even strings that had, say, 12 or 15 characters. Okay? So this is not okay. Sometimes you can get away with brute force search. Alignments is not one of those cases. So instead, we need a fast, non-trivial algorithm, some algorithm which is sort of clever. And once again, when you've finished the dynamic programming boot camp through which I run you in weeks roughly 8 and 9 of this class, this will be a totally, totally routine problem. Okay? So it's really just a completely canonical application of dynamic programming. Okay? Again, I want to emphasize that had there been no alternative to brute force search, had there been no clever algorithm for computing the NW score, genomicists would not use the NW score for computing similarity among strings. Okay? They would use something else. Computational genomics, I'm sure, would still be a very successful field, but it would not look quite the same. Okay? The fundamental definitions would be a little different if you didn't have these kinds of algorithmic tools that you're going to learn in this class.